Hello, everybody. This is Mechanical NeRFs for Agricultural AI, presented by me, Aaron McAfee, and Thomas Pluck. In the problem and motivation, real-world agricultural data is really scarce and costly. Therefore, we use synthetic data to replace real data, but this causes the real sim gap. Therefore, there's a need for realistic synthetic plant data that incorporates dynamic lighting and mechanics. Our contributions consist of the following. We do a comparative analysis of 3D Gaussian splatting and material point method, and we compare that with radfoam and position-based dynamics. We also develop a work-in-progress plugin for editing radfoam models. We do the data capture using RealSense D405 adapt cameras. We have a static set up in the Manuf Robotics lab for data capture for the purpose of physics modeling. And then we use a free range camera around the plant where we're trying to capture as much novel views as possible for the static modeling. We trained a 3D Gaussian splat on our captured data, and here are our results. We also use the Unity plugin to edit the 3D Gaussian splats so that we could remove the background. We also developed a segmentation pipeline where we use YOLO V8 to detect the panicles, and then we use decoupled SAM segmentation to get the segmented out panicle, and we use the multi-view photon algorithm to then get to essentially one-hot encode the points of the model.
The second NeRF model we compare against is radfoam, a differentiable 3D Voronoi mesh that is rendered using an efficient ray matching algorithm as opposed to the typical rasterization method used with Gaussian splatting. While training with radfoam takes significantly longer, from 5 minutes up to 5 hours, its potential is in providing an efficient neural substrate for real-time dynamic relighting and other inverse rendering techniques which challenge popular NeRF models today. Compared to our Gaussian splatting model, we found that radfoam performs consistently worse than Gaussian splatting while taking longer to train. For the mechanical portion of this project, we ran PhysGaussian, which combines Gaussian splatting with the material point method, and found that on a commercial NVIDIA RTX 3060 Ti with 12 gigabytes VRAM, that it produced approximately 3 to 4 frames per second for simulation. This low speed motivated the search for a more efficient algorithm that would allow for physics in neurally generated 3D reconstructions. The Voronoi structure of radfoam naturally lends itself to implementing faster physics algorithms typically used in modern game engines called position-based dynamics. Unfortunately, while we did not have time to implement position-based dynamics itself, we did have time to implement the preliminary editor software that allows users to edit radfoam meshes on the fly and isolate objects either as game assets or for downstream physical simulation, such as using PVD. Our project can be found on GitHub. The segmentation pipeline and NeRF processing can be found in a GitHub hosted by Aaron called SynthPlant3D, and the Unity Radfoam editor, forked from Christian Schott's Radfoam Unity, can be found at Thomas Pluck MU, Radfoam Unity. We would like to thank you for taking the time to watch our presentation.